Okay, welcome back. So we just did the last video. We did a couple of examples of hypothesis testing. This is the essence of inferential statistics, and so I want you to put your thinking caps on a little bit for this video because we're not going to do any computations. But once again, this is conceptual stuff, so we'll need to think about what we're doing here. So basically, when we do inferential statistics, we are making a guess about something, an inference. But this is not just a random guess, of course. This is guesses or making a decision, about our null hypothesis based on the data that we collect. So it's a little bit inaccurate to just say, well, we're guessing, because these are educated guesses based on data that we collect from an experiment. So I want to talk about the nature of making guesses and the fact that when you aren't sure about something, even when you have data, you need to entertain the possibility that you're making a correct decision or that you might make an incorrect decision. So let me give you an example of how this might work. I could ask someone, I could put them in a room with no windows and no doors, and I could say, well, do you think it's raining outside? Okay. That would be a guess for them. And of course, their guess could be based on whether or not they can feel the humidity, whether they paid attention to the news the night before, whether they had just come in from being outside, whether they, whatever. I mean, they could make their decision based on a bunch of information. But what I want to emphasize here is if you're in a room with no windows and no doors, you can't hear anything, then you really don't know if it's raining or not. Okay? I'm going to ask you to make a guess. But there is a reality. Okay? There is a reality that is independent of how you guess, what you're going to guess. So in this case, I'm going to put the reality. Let me fix this a little bit here. I'm going to put reality here, okay? And so the reality would be that it is raining or that it is not raining, okay? That's the reality. Those are the two states of reality, okay? And what I'm going to do here is I'm going to make a 2x2 matrix. And whenever a professor makes a 2x2 matrix, pay attention, okay? Because this is a very common form of, decision making. When you do a Punnett square in biology for genetics, we do this 2x2 to sort of cross two different states of the world, I suppose, okay? In this case, I'm talking about reality. It is either raining or it's not raining. Those are the two possibilities. We could also talk about this, perhaps as the truth, okay? What is really happening, okay? Now, the other part of this 2x2 matrix is the individuals, let's say their inference, okay, their guess, their decision, and so there are two possibilities here as well, and that is the person either says that yes, it is raining. I mean, that's one possible guess, right? If I were to ask you, do you think it's raining outside? And by the way, the decision or the guess, I don't know, is not acceptable, right? We're going to force people to either say, is it raining outside or isn't it raining outside? When I put this into terms of research, I'm going to say, do you think the drug had an effect or do you think it didn't have an effect? Or do you think that this treatment worked or this treatment didn't work? Okay? So if you say, I don't know, it's kind of not a, it's, of course you don't know. You're trying to make an inference, okay? So one of the possibilities is to say, yes, it is raining. And the other possibility is for you to guess that it's not raining, okay? Now, you don't see reality. You're in this room without any doors or windows. And so you don't know what the truth is. You don't know what is really happening. And I'm asking you to guess whether it's raining or not. Okay? So in this situation, then, there are four possibilities in terms of how your decision matches with reality. Okay? So let's go, then this is what's making up our 2x2 matrix here. Okay? So let's look at this. Suppose in reality that it is raining. And your guess was that it is raining. Okay? In that situation, then, the person would be correct. Okay? Because their guess about what's going on in reality matches reality. And so that would be correct. Or we could call this a hit. Okay? There's another possibility, though. If the person says, yeah, I think it's raining, but it's not raining, okay, well, then this would be an error, right? Then we could call this a miss. Okay? So when you make your decision, you say, I think it's raining. You're correct if it really is raining. But if you say it's raining and it's not raining, then that's an error, sometimes called a miss. Okay? Likewise, we can make a decision. It's not raining. Okay? Well, if you say that it's not raining, but it actually is raining in reality, you say it's not raining, but in reality it is, then this is called an error as well, a miss. Okay? Now, somebody might say, well, why would you say it's not raining if it really is raining? It's because you don't know what reality is, right? You're in that room, no doors, no windows, okay? So based on whatever you're making your guess on, you can guess that it's not raining. But if it is, then that's an error, okay? A miss. But you could say that it's not raining, and if in reality it's not raining, then of course you're correct here, or we could call this a hit, okay? And so whenever we're matching a decision, an inference, a guess, against reality, we're going to get this 2x2 matrix. And there are two ways to be correct, and there are two ways to make an error. Okay? Again, you don't know what reality is, so you're making these guesses, and then we have to sort of compare that. Now, I call this a hit. When you're correct, a hit. When you're incorrect, a miss. I'm assuming that some of you have played the game Battleship. Have you ever played that game? It's really interesting because most of the time when I ask people if they've played that game, most people have. It's just like kickball. Everybody has played kickball. Everybody's played Battleship. But let's think about Battleship. It's kind of an interesting game relative to this matrix, right? You have your ships in certain places, and your opponent can't see where those ships are, okay? And so they make guesses about where the ship is. Of course, with Battleship, it's difficult because you're not basing your guesses on anything, really. Typically, you're just sort of randomly guessing. You know, you say, I think your ship is on G2. And then the person looks and they look at their position of their ship and they say, oh, it is on G2. So they say hit. And then you put your little peg in there, right? Or you could say, I think your ship is on G2. And the person looks and it's not on G2. And so they'll tell you it's a miss. Okay? So this is the reality of where the person's ships are. This is your guess. And just like we have different combinations here, you could be correct if you guess the same position that your opponent has that ship, and you can be incorrect if you guessed a different position. It's the same thing here, okay? When we're doing inferences, we're making guesses, all right? And you can be, you can have errors and you can be correct. And let's stay with the weather. Let's keep with the weather because this is one of my little pet peeves, especially here in upstate New York. Here's a little inferential game, okay? Here's a little inferential game. So let's do reality. And this has to do with predictions of weather, okay? So let's say the reality is the snowstorm shows up, or the reality is no snow, okay, or no snowstorm. And here is the meteorologist prediction, okay? So this is what the meteorologist is going to predict. Either that the snowstorm is coming, or that we will get no snowstorm. So this happens Monday night, and then let's see what happens on Tuesday, okay? We can compare what happens. And so if the meteorologist predicts a snowstorm, and a snowstorm actually comes, well, that's good. I mean, in terms of the prediction, right? The meteorologist was correct. What if the meteorologist predicts a snowstorm, but no snowstorm comes? Well, that's an error, okay? But before we get on the meteorologist case, just hold on, okay? So the meteorologist could also predict no snowstorm, and the snowstorm comes, and so in that case, that's an error as well, okay? Or the meteorologist could predict no snowstorm, and no snowstorm comes, and of course, that would be correct as well, okay? Now I'm going to ask you a question here. I'm going to ask you a question. Of course, we want to be here or here, right? Of course, we want to be correct. I want to be correct when I'm making any guesses. I want the weather person to be correct when they're making a prediction about the weather, okay? That's a given. We want them to be correct. Hopefully they're correct a lot of the times. There are two errors here. There are two different kinds of errors. The meteorologist could predict no snowstorm, but a snowstorm comes. They could predict a snowstorm, and no snowstorm comes. Okay? We want to be correct. Did I already say that? We want to be correct? Of course we want to be correct. We want to be here or here. We want to predict a snowstorm if it's coming. I want to not predict a snowstorm if it's not coming. Okay? That's a given. But of the two errors, if the meteorologist is going to make an error, which one would be a better error to make? Now, when I ask this in class, sometimes people say, well, I don't want to make an error. I know nobody wants to make an error. We want to be here, right? But if you're going to make an error, is there a better error to make or not? Let's think about the two errors. Predicts that no snowstorm comes, but a big snowstorm comes. That's an error. Predicts that a snowstorm is coming, but no snowstorm comes. That's an error as well. Okay? Which one is the better error? Well, I would argue, I think most people would argue, it's better for the person to predict a snowstorm and have it not come than predict no snowstorm is coming and a big old fat snowstorm comes. Okay? Everybody with me? I want to be here or here. But if I'm going to make an error, I can make a decision about an error. I can make a decision about an error that's better or worse. Predicting a snowstorm that never materializes is a better error. Okay? Because people will be safe, people will get supplies, people will take it easy, people will leave earlier in the morning if somebody predicts a snowstorm. Then if none comes, oh well, okay? It's a better error than not predicting any storm and everybody getting caught in the storm, okay? Folks, this is basic general education because I get really annoyed many times when people are like, oh, they predicted a storm, it never came. Oh, they predicted another storm, it never came. Well, meteorologists actually learn in school when you're making a prediction, bias yourself toward predicting a storm. If it doesn't come, okay, that's fine. I want to be correct. This is a better error, okay? Certainly, the meteorologist wants to be here or here. But if you're going to make an error, this is a better one to make, okay? So we're going to talk about that in terms of research decision-making as well. With research decision-making, you can make two correct decisions, and you can make two errors, okay? So let's take a look. Let's take a look at the errors that you can make when you're doing decision-making in research. Okay? So let's make our 2x2 matrix. Let's make our 2x2 matrix, okay? Now, let's see. I'm going to make this, we'll talk about this as reality, right? And let's do this as a generic. I'm going to say this. I'm going to say the treatment works. Could be a drug treatment. It could be when we gave our caffeine to our word search people. It could be the CD. You know, when I say treatment, I don't necessarily just mean medical treatment or something like that. Whatever it is that you're imposing on the group, whether it's listening to the CD or taking caffeine, or I'm going to put red food coloring in your water, okay, whatever that is. You see, it works, that means it's going to make a difference, okay? Or the other reality is that the treatment does not work. Okay? But remember, when we make our decisions, we're always making the decisions based on the null hypothesis, okay? I want you to take your time and think this through. If the treatment works, that means the null is false. the treatment works, that means the null hypothesis is false. Everybody with me? You need to be comfortable with this. If you try to memorize it, damn it, you're going to get confused, okay? I know that you're capable of thinking this through, all right? If we say that the treatment works, that the red food coloring made a difference, that means that the null hypothesis was false, okay? If the treatment does not work, then that means that the null hypothesis is true, okay? If the treatment does not work, that means our null hypothesis is true. If the treatment doesn't work, the null hypothesis is true. Or we could say, if the null hypothesis is true, there is no treatment, right? Okay? Everybody with me? Treatment works, that means the null is false. Treatment does not work, that means that the null hypothesis is true. Okay? Just like we talked about, guessing whether it rains or not, okay? The researcher doesn't know reality. The researcher doesn't know reality. If the researcher knew about reality, why are you doing research, right? You know what reality is. The researcher is trying to guess about reality, trying to guess what's in that canvas bag, okay? So here is the researcher's decision and what have we been doing? I mean, the last 3 examples, the last 2 videos, we did our hypothesis testing, okay? And remember step 4 is we make a decision about the null hypothesis, okay? Please think this through, okay? So one of our decisions, one of our options was we reject the null. And if we reject the null, we're suggesting that there's a treatment, okay? If we reject the null, we said, hey, the red food coloring made a difference. If we reject the null, we're saying, hey, that CD caused increases in sales. If we reject the null, we're saying that the treatment worked. We could also fail to reject the null, okay? We did that with the caffeine example. We said, hey, this caffeine doesn't look like it affected the completion time, okay? Reject the null, fail to reject the null, okay? This would imply that there's a treatment. This would imply that there is no treatment, okay? This is why it's nice to think about the rain, whether it's raining or not, and whether the person says it's raining or not, because that's an easier matrix to conjure up and think about. This is exactly the same concept. It's just that it's a little bit more difficult because we're talking about the null hypothesis and rejecting the null and failing to reject and all that stuff. Take your time, okay? Stand still. Stand still. Look at this. Think this through. Once we fill in the matrix, what you should do is start anew and see if you can fill in the matrix the way we've done it here, okay? Then watch the video again. See if you've done it correctly, okay? Let's look at the possible outcomes in terms of hits and misses, in terms of being correct and not correct, okay? Even though we don't know what reality is, right? We still did our matrix with the raining example. We don't know what reality is, but we can talk about the possible outcomes. We can talk about these possible outcomes, okay? Even if we don't know reality. So, if in reality the treatment works, if in reality the treatment works. That is, the null hypothesis is false. And the researcher rejects the null. If the researcher rejects the null and the null is false, if the researcher rejects the null, she is implying that there is a treatment. If there is a treatment, we reject the null. So this becomes one of our correct quadrants here, okay? This is a hit. Experimenter rejects the null is false, cool, okay? I don't use the cool beans phrase, but if you want to, feel free, cool beans, cool. The researcher's decision matches reality. We never know if this is the case. We don't see reality, okay? But we can entertain the notion that we made the right decision. If the researcher rejects the null, that is, they're implying that there's a treatment effect, but the treatment does not work. That is, the null is true, but the experiment is rejecting the null. Well, of course, then, this is an error. This is a big fat miss. And it's not cool beans, okay? Researcher doesn't know if she's in this quadrant either. We'll talk about why that's okay, but we can at least entertain this. So let's fill in the rest. Researcher's decision is to fail to reject the null. If we fail to reject the null, then I'm saying there's no difference between the treated and the normal. If I fail to reject the null, I'm saying there's no difference, okay? If the treatment really works, that is, the null hypothesis is false, and I fail to reject that null, well then, of course, this is an error as well. This is a miss, okay? Now, sometimes people will be like, well, why would you fail to reject the null if the treatment works? Listen, folks, the researcher doesn't see this, okay? The researcher doesn't see this. She is making her decision based on the data, okay? You can make a wrong decision. I talk about this a little bit when I talk about a court case, right? I mean, the reality is the person committed the murder or they didn't. I mean, reality is the person committed the murder or they didn't. Now, what we want to see happen is the jury make the correct decision, okay? If the person did commit the murder, we want them to say guilty. But if the person didn't commit the murder, we want them to say innocent, right? Sometimes in a trial, what happens is the jury says guilty because the evidence makes it look like the person committed the crime, right? Because the evidence made it look like it. But if the jury says guilty and the person did not commit the crime, that's an error. What is the other error? If the jury says not guilty and the person committed the crime, then that's an error too. So the way you think about this with a jury is that it doesn't matter what the jury's decision is. It matters whether the jury's decision matches reality. The jury's decision matches reality. And that will be based on the quality of the data. That is the evidence, right? In a court of law, we call data evidence. If we're doing medical research or if we're doing psychology stuff, we call it data. But data is evidence, is information, is data, is evidence. It's all the same, right? We want to make our decision based on information, based on evidence, based on data, and we can always be wrong, potentially. If we fail to reject the null, we don't have enough data to say that this group is different from the other group, okay? If we go back to our caffeine example, we failed to reject the null, okay? But it could be that we just had people that were insensitive to caffeine. We could have had a weird sample. We might have been wrong. I'm still going to say this based on the data, but we have to acknowledge that we could potentially be wrong, okay? And we'll talk about these errors in a minute. Okay, so the fourth possibility here is the experimenter fails to reject the null, just like we did with our caffeine example. We say, I don't think there's a treatment, okay? If in reality the treatment doesn't work, if in reality the caffeine doesn't affect completion time, well then of course we have another possible correct decision, another hit in this case. Okay? This is the way it works with decision making. You make your decision based on incomplete information. The meteorologist is trying to predict whether or not we're going to have a snowstorm. Incomplete information. The pressure, the wind, the temperature, when we've seen this pattern in the past, blah, 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 blah. We think there's going to be a storm. They could be right, they could be wrong. They know that, okay? When I ask you to guess whether it's raining out or not, you may have very little data, and so the chances that you're going to be incorrect are even more. When we're doing research, we get as much data as we can, and then through our 5-step hypothesis test, we're going to make one of these decisions, and regardless of which one that you can make this decision, and either you could be correct or you could be wrong. You can make this decision, you could be wrong or you could be correct. Okay? Since we don't know this, how the hell are we doing all of this? Well, we'll take a look. Okay? In this case, in science, in medical research, we of course want to be here or here. Everybody with me? Of course we want to be correct. Of course we want to be correct. We want to be correct. We want to be correct, okay? But just like with the meteorologist, one of these errors is not like the other in terms of its seriousness, okay? Let's focus on these errors a little bit more. We reject the null, but really the treatment didn't work. We rejected the null, treatment didn't really work. That's an error, okay? In science, we call this the type 1 error, okay? What's the other error? We fail to reject. We say, I don't think there was a treatment, but the treatment worked, right? We failed to reject the null, but the null is false. This is called, anybody guess? Type. Hey, I heard somebody say type 2. Very good. Not really, there's nobody here. Type 1 error, type 2 errors. I'm sorry that it's not more creative, but I don't think people want an error named after themselves. Okay? Now I'm going to ask you, which one do you think is worse in science? Which is the worst error? Which is the better error? And sometimes people have a hard time, like, well, I don't want any error. Yes, I don't want any error either. Okay. But just like the meteorologist, there's one that's better than the other. Well, in science, this one is thought to be the worst of the two errors. This one is thought to be the worst of the two errors. Okay? Let's think about why that is. What's going on here? The experimenter says there's a treatment, but in reality there's not. Okay? The experimenter rejects the null, but in reality the null is true. Okay? And again, let's talk about this again, because I know it takes some time. Why would the experimenter reject the null if the null was true? Well, if we have a sample that ends up being out in those extremes, if we have a sample that's out in those extremes, it happens once in a while, even when the treatment doesn't work. Okay? So it may be that the red food coloring really doesn't make a change, but it looked like it did. We rejected the null, but the null is true. That's a type 1 error. That's seen as more serious or more bad, I guess, if you want to say, this type 1 is worse than the type 2 because of the way science works. It works as an accumulation of information from one group of scientists to another, to another, to another. What this error represents is us saying that the treatment worked when in reality it didn't. So that can send us down a wrong path quickly. And when we talk about the cumulative nature of science, I'm going to base my research on your research. You base your research on somebody's previous research. And so we don't want to have kind of a false claim that the treatment worked when all of a sudden we find out maybe later that it didn't work. That's going to send people down the wrong path quickly. Okay. What's happening with the type 2 error? What's happening with this type 2 error? Well, the researcher says, I don't think that the treatment had an effect, but in reality it did. So that's an error, okay? The reason that this is not seen as problematic in the sciences is because, well, you're sort of you're missing the treatment, right? You're saying that it doesn't work when in reality it does. The assumption there is some other scientist will find out that the treatment works. This will be caught. This one will send us down the wrong road in science, okay? So in science, type 1 error is seen as more serious than the type 2 error, okay? So, and of course, we definitely want to be correct, okay? Now, even though we don't know what reality is, we can entertain different models for reality. And what I want to show you here is the probability of making a type 1 error, the probability of making a type 1 error. And I'll show you how that works, okay? Let's do this, because I may need this again, but hopefully you have this in your notes, okay? So when I talk about this next part, you can look at it in your notes. Here's what happens. So I'm going to talk about a reality where the null is true, okay? So if we talk about our normal population, and when I say normal here, I'm saying not treated. So this would be the normal sales at the seafood restaurant that is without any special background music. It will be how people finish their word search without caffeine. It will be how people are reading that 4% clear sucrose solution, okay? And so the non-treated will have a mu and a standard deviation, right? A mean and a standard deviation, okay? Remember step 2. Remember step 2 in our hypothesis testing procedure. What did we do in step 2? We said, listen, we set alpha at 0.05. We said anything above a z-score of 1.96 or below a z-score of 1.96. If we found our samples in there, we would reject the null, okay? Now, I'm playing God here. I'm just going to say, let's assume that the reality is the null is true. There is no treatment. There's just one curve. If the null was false, by the way, if the null was false, we'd see another curve out here, or a curve here. That is, this would be the red food coloring curve. This would be the clear curve. This would be the caffeine curve. This would be the no caffeine curve. This would be normal sales without ambient music. This would be sales with ambient music. Okay? So I'm just dealing with, this is a representation of one reality. The null is true. So the researcher sets these points, says, I'm going to reject if anything is above there or below here. I'm going to say, wow, that doesn't look like it belongs to this distribution. So here's God. We're playing God. We know what reality is. The poor researcher is doing the work, okay? And she does some kind of a treatment and ends up getting this sample, okay? Let's do a sample distribution here. If the researcher gets this sample, so this is a z-score, let's say, of minus 1.07, just making that up, folks, okay? If the researcher gets that sample, what is the researcher going to do? Reject the null or fail to reject? That is correct. They're going to fail to reject the null. Fail to reject the null, okay? If this is the reality, and I fail to reject the null, then we're good. We're correct, okay? Let's move on. If the researcher pulls out this mean, here's a z-score of 0.87. Reject the null or fail to reject? You'd fail to reject the null, right? Because it doesn't go into this area. You fail to reject here, you fail to reject here. If you fail to reject and the null is true, we're good to go. Here, lots of here's. Out here, reject or fail to reject? Fail to reject the null, okay? And that matches reality. But once in a while, the researcher gets this sample. The z-score here is 2.17. What is the researcher going to do? Reject the null, right? The researcher is going to reject the null because it went beyond the area where you said you were going to reject. The researcher rejects the null, but we're talking about this reality, folks. So in this case, that would be a type 1 error. I rejected the null, but this came from a non-treated distribution. That's how we're going to make our mistake, okay? If we get this sample, not going to make a mistake. This sample, correct. This sample, correct, correct, correct. If we get this sample, we're going to reject the null, but the null is true, okay? In fact, anything in here, if this is the reality, I'm playing God. I'm saying, let's consider this the reality. What percent of the time will the researcher reject the null and it's a mistake? What percentage of the time in this example? 5%. Okay? Correct decision here, correct decision here, correct decision here, correct decision here, correct decision here. Okay? As soon as we go in here, we're going to make a mistake. Okay? Hey, this is like when I said I don't think a meteor is going to hit this room, and all of a sudden, boom, it hits the room. I mean, oops, that's not going to happen very often, but I'm going to make a mistake when I say that's not going to happen. These are unusual cases where we're going to make a mistake, okay? And if we go back, let me grab go back to your notes. We know the probability of making a type 1 error. The probability of making a type 1 error is equal to our alpha level. We're normally going to set the alpha level at 0.05. What we're saying is, even listen carefully, okay? Even when none of these people are treated, okay, once in a while, I'm going to get a sample that looks like it was treated. Even when none of these are treated, once in a while, I'm going to get a sample that looks like it was treated. That's why we have to be careful, okay? 95% of the time, I'm going to be good to go. But in this case, if we set our alpha level at 5%, 5% of the time, we can make a type 1 error. But listen, folks, that's not a large percentage. I wish I could make all of my decisions so that I would make a mistake only 5% of the time. I make mistakes way more than 5% of the time, okay? So this is pretty good for researchers. So when you read a study and they say they found an effect, you can be 95% sure that they're correct. But once in a while, 5% of the time, we're going to make a type 1 error, okay? If we have our alpha level set at 0.05. If we have the alpha level set higher or lower, that's going to affect the probability of making a type 1 error. Scientists have agreed to sort of accept the fact that they're going to make a mistake 5% of the time. That's set by the alpha level. Okay. The probability of making a type 2 error is dependent on a lot of different things. We know what this level is. This level is variable, and yeah, we may talk about that in the next video. I'm not sure because we have to think about an exam this week. But let me think it over. I may skip the probability of this part for now so we can get through other things. But probability of making a type 1 error is 5%. When we go back to our conclusions, that p less than 5%, you're also acknowledging to the reader that the chances that I made a type 1 error are less than 5%. They say less than 5% because the z-score is greater than 1.96 or less than negative 1.96. Okay, if I have a z-score of 2.37, then I'm going to say the chances that I made an error are less than 5%. That's where that comes from. So it's the probability that the null is true, and it's also the probability that I made a type 1 error. Pretty low when people are claiming they have a treatment effect. Okay? Watch the video again if you would like. Read it in the book. And think it through, please, because if you start memorizing this stuff, rejecting the null, failing to reject the null, what if I fail to reject, but it's really true and it's false, but I do, right? You're going to get messed up. Take some time with this. See if you can recreate this once you put it away, and think it through. Please email me if you have questions. Okay, if you have questions, email me, and see you at the next video. It'll be Tie-Dye Friday. Hope everyone's safe.